Yeah, so I will be, okay, as many people here, I am interested in combinatorial algebraic geometry, so I like it when combinatorics and algebraic geometry interact together, and I especially like it when they interact together with something else. And in this case, our object of study will be the KP equation. So K and P are names, and the equation is a partial differential equation that describes the motion of water waves, like the ones in these pictures here. So generally they're shallow water waves, and other properties. Here's the equation, and the function P records the height of the wave at space coordinates x and y and time t. And we are interested in solutions of this form. So they come from a function tau, which satisfies what's called the Hirota's differential equation, or sometimes Hirota's bilinear form. And you may not believe me, but this is a simpler expression in some ways than the actual KP equation. And so once we find tau functions that satisfy this, the resulting P satisfies the KP equation. And I will be talking about how we can construct tau functions. One way to do it is from algebraic curves, and another way from Grassmannians. So one is the first is due to Krichever, and the Grassmannians is due to Sato. Okay, so first I'll talk about Grassmannians. So these are going to be a specific class of solutions called soliton solutions. So we consider tau of this form. So most of this stuff isn't important for this talk. What we care about are these PIs. So they're indexed by subsets of size k of 1 through n. And these are PIs. And Sato showed that functions of this form are solutions to Hirota's differential equation, and therefore give solutions to the KP equation if and only if the PIs are actually Plücker coordinates. So the points lie in the point PI, indexed by all these i's, lies in the Grassmannian GRK, n. And then we can call a function tau that has these hyperparameters and the fixed k and n, a kn soliton. And of these solutions, the real and regular solutions are the ones which are physically relevant. And these actually correspond to points in the positive Grassmannian. And if you've heard of the positive Grassmannian, then you know that this is very interesting to a lot of combinatorialists. And so in particular, the positive Grassmannian can be divided into cells called positroid cells. And these are indexed by a multitude of combinatorial objects like Lie diagrams, playback graphs, and so on. So all of these things. So now that's a natural point of study to think about how the solution behaves depending on which combinatorial objects it is related to. So Kodama and Williams did that. So they studied the combinatorial structure of real and regular soliton solutions and their relationship with the positive Grassmannian and positroid cells. And I guess I didn't say what the positive Grassmannian is. So it's the subset of the Grassmannian. It's a semi-algebraic set where we take all of the PIs to be non-negative. And this is, in particular, non-empty and interesting.
But are we supposed to know what positroid cells are, or?
No, I don't have time to discuss it. If you know, then it maybe means something to you. But otherwise, if it sounds interesting, you can read about it. Okay, so now the other perspective is starting from algebraic curves, and here we are interested in Riemann theta functions. So given a curve of genus G, it has associated a Riemann theta function. This is a complex analytic function depending on Z in CG and a matrix B which is a Riemann matrix of a curve, also sometimes called a period matrix of a curve. So this is a G by G symmetric matrix. We can choose various normalizations. We choose negative definite real part. But it's a matrix that records important data about the curve and its periods. And I don't have time to go more into detail about that, but the important thing here is that this is a function that depends on a matrix, and once you fix the matrix, you get an infinite sum of exponentials ranging over the entire integer lattice of dimension G. Okay, and so Creature showed that finite gap solutions to the KP equation can come, they come from theta functions. So this is the same expression that I had a couple slides ago, except now that what used to be a tau is now a theta function. And theta is just a function of one variable z, whereas our tau takes in an x, y, and t, but we can fix that by adding parameterizing variables u, v, and w. So ux plus vy plus wt replaces z here. And so I say here we have degree G non-special divisors on algebraic curves. So the data of the divisor tells us information about these u, v, and w.
So finite gap means?
That's a statement about the spectral data of the solution, so it has a finite number of spectral gaps. But also it's a type of solution, it's a class of solutions that's important. Okay, and then again, we might be interested in which of these are physically relevant. So these would be the real and regular finite gap solutions. And so de Broven and Nathanson showed that real and regular finite gap solutions correspond to divisors on, now they're not just genus G curves, they're genus G M curves, which are, so M curve means maximal curve. This is a curve that achieves the Harnack bound on the maximal number of real components, which is genus plus 1. And then we have a degree G divisor, so 1 point. So there will be 1 point of a divisor on each G of the G plus 1 ovals on the curve, and then a marked point, and that gets subtracted to give us a a degree G divisor. Okay, but all of that also doesn't really matter. What's important here is that we have a special situation going on in the real and regular case. Okay, and now I will talk about two degenerations very briefly. So these are more recent results. So these are earlier in the last century. And these are in the recent decades or decade. So Abenda and Grinovich studied real regular soliton solutions and showed that any real regular soliton solution can be obtained as a limit of real regular finite gap solution. So what they do is from the soliton data of a real regular soliton solution, so a point in the positive Grassmannian or a positroid cell in the positive Grassmannian, they can assign to it, they have a way of assigning to it an M curve that degenerated and or perturbed in a convenient way gives you the real regular soliton solution and the limit. Another degeneration, which is past work with Daniele Agostini, Claudio Fevola, and Bernd Sternfels, we obtained soliton solutions to the KP equation from tropical degenerations of smooth algebraic curves. So departing from M curves, and this is going in the other direction, we start with curves, do the tropical degenerations, and we showed that we obtain soliton solutions. I'll give a little more detail on that. So the main idea here is that we work over a non-Archimedean field like Puiseux series. So you can think of a curve over such a field as a family of curves that depend on a parameter. And when the parameter is non-zero, our curves are smooth. When the parameter is 0, we see nodal singularities. And so really, you can also think of as us trying to find a way to assign solutions to the KP equation starting from nodal curves. And then we study what happens to the Riemann matrix, and then the Riemann theta function, and then the tau function and the KP solution in this limit. So the theta function becomes a finite sum of exponentials. It used to be infinite, but now it's supported on a very special set called the Delaunay set. I will not be defining this, but these are very special sets.
You want to degenerate as degenerate as possible component of genus 0.
Sorry?
This nodal curve, you want it to be as degenerate as possible. No component of positive genus. So.
No. Yeah, we're working with rational. Okay. And then the function, so the theta function becomes a finite sum of exponentials, and the solution to the KP equation that comes from this degenerate theta function becomes actually a soliton solution of the KP equation. And we define a variety, which we call the Hirota variety, parameterizes all solutions of this type associated to a particular Delaunay set. Okay, and what I mean, just say a little bit about these degenerations. So here I have the five types of tropical limits in genus 3. So here I have my genus 3 nodal curves. And the way that you can draw their metric graph, which is their tropicalization, is each component gives you a vertex and each intersection gives you an edge. So self-intersection is a self-loop. And then, so this one, for example, we have 2 components, that's 2 vertices, and then one has 1 self-intersection, and then 3 intersections with the other one. The other one has no self-intersections. And then with this and some other data, you can pretty easily get the tropical Riemann matrix Q, which will be a G by G symmetric positive definite matrix. And then you can write down the degenerate Riemann theta function. Again, this set is a Delaunay set associated to Q. I'm not defining that again, but just these are very special sets. Then the degenerate theta function is this finite sum of exponentials. And then I can pull out all of my kind of unknown parameters, so these A's, U, V, and W's, and look at all such points in this product space such that the resulting tau actually gives us a solution to the KP equation. And the space is called the Hirota variety. So every point in the Hirota variety corresponds to a tau function, which is a solution to the KP equation. And then by studying the Hirota variety, we, in certain cases, so in joint work with Claudia Fevolo, we studied this for the case of irreducible rational nodal curves. And we were able to find explicit expressions for the soliton solution. So again, we're interested in what these PIs are, so the actual point in the Grassmannian. So this is represented by a matrix, and here I've just pulled out a table. So here we have a genus 3 irreducible rational nodal curve. And then here we have the different normalizations. So if we pulled this out and flattened it into a P1, the arcs here represent how the nodes are connected. So these 2 points together form one of the nodes, these form one, and these form one. And then we have associated to it a matrix. So I here, unfortunately, have expressions that I don't explain, but these ratios, you can just think of them as general parameters that we can vary, lambdas. And you can see as you vary lambda and make them all positive, then this covers a positroid cell, if you know what that means. And then these are the various positroid cells covered by this one nodal curve. And if I gave you time to stare at this table for a little while, you might notice some patterns of how these matrices look compared to the graphs that I drew. And one thing that we would like to do or are interested in general is how to, in general, start from a positroid cell and know which which nodal curves are associated to it. And create a dictionary in general, a general rule to associate a positroid cell to a nodal curve in the way that we can do it. And so in a forthcoming work, joint with Simonetta, Benda, Turku Zlimchuk, and Claudia Fevela, we do this for genus 2 and 3 curves and hyperelliptic curves, irreducible rational nodal curves. This will hopefully be out in the coming months. And there's a lot more interesting things to do here. In general, we want to find the ways to bring all of the things that I talked about together. So these M curves, positive Grassmannian, and the various degenerations. There's a lot of links hiding there that we want to discover. That's all. Thank you.
Question?
I'm not sure whether you said something about this and I missed it. But you have this shallow water equation, which is just a PDE, right? It has Solomon solutions, and you identified kind of two families that have this algebraic origin. Are there others? I mean, what is special about these, or do these span all of the Solomon solutions of this equation?
Yeah, so all of the solutions live in what's called the Sato Grassmannian. This is an infinite dimensional Grassmannian.
Okay.
And yeah, so you can put all the solutions to the KP hierarchy, actually, in accordance with this infinite dimensional Grassmannian. And then as you get more specific in your classes, you get more specific with your types of solutions. But yes, so the soliton solutions, a definition of them is that they come from points in a finite dimensional Grassmannian.
Use that as a definition of a Solomon solution.
That is a definition.
I see. I thought of Solomon solutions as being ones where time and space are
Yeah,
affine relation.
that's another one.
Are they equivalent?
Yes.
Those are equivalent there. I see. Okay. So it's a very vague question, but if we look at this, if you give me this PDE, physicist comes and gives me this PDE, I wouldn't necessarily see it as anything to do with algebra. Is
Yes.
there a reason?
Well, I guess that's kind of what's amazing about Kricher's work was that he found this connection with algebra.
That should not be obvious to us.
No, absolutely not.
What is Sato's Grassmannian?
It's kind of complicated. Well, okay, so it's an infinite dimensional Grassmannian, and it has a definition that I can't say off the top of my head.
Okay, so I think we'll thank Yelena again.